Today we prove why generalized eigenspaces decompose the whole space. And we do it in a way that stays firmly inside linear algebra. So the goal is a clean direct sum theorem, not a sightseeing tour through unrelated bureaucracy wearing Greek letters. Let V be a finite-dimensional complex vector space. Let T be a linear operator on V. And let n be the dimension of V. Write lambda 1 through lambda m for the distinct eigenvalues of T. Over the complex numbers, we are allowed to expect eigenvalues instead of emotional disappointment. For each eigenvalue lambda, define the generalized eigenspace G of lambda, T to be the null space of T minus lambda I to the n. Our goal is to prove that V is the direct sum of these generalized eigenspaces. In other words, every vector splits uniquely into its generalized eigenvalue pieces. Even vectors apparently need administrative categories. The whole proof rests on one lemma called the fitting decomposition. For any linear operator S on V, the space V splits as the direct sum of the null space of S to the n and the range of S to the n. One part is eventually killed by S, and the other part survives inside the image. Remarkably civilized behavior for a linear operator. To prove the lemma, define Nk to be the null space of S to the k, and Rk to be the range of S to the k. The null spaces form an increasing chain, and the ranges form a decreasing chain. Finite dimension now does the heavy lifting, which is nice because it rarely complains about overtime. Because V has dimension n, neither chain can keep changing forever. By step n, both chains have stabilized. So the null space of S to the n equals the null space of S to the n plus 1. And the same holds for the ranges. Take a vector V in the intersection of the null space of S to the n and the range of S to the n. Because V lies in the range, we can write V as S to the n of some u. Because V lies in the null space, S to the n of V is 0. That gives S to the 2n of u equals 0, so u lies in the null space of S to the 2n. But the null space chain has already stabilized. So the null space of S to the 2n is the same as the null space of S to the n. Therefore S to the n of u is 0. And V is 0. So the intersection is trivial. Now apply rank nullity to S to the n. The dimensions add up to the whole dimension of V. Trivial intersection plus full dimension gives the direct sum decomposition. The lemma is proved, and for once the notation actually earned its salary. Now take S to be T minus lambda 1I. The fitting decomposition immediately gives V equals G1 direct sum R1, where R1 is the range of T minus lambda 1I to the n. So G1 has been split off cleanly. We have extracted the lambda 1 part without any mysterious ritual involving determinants and candles. The subspace R1 is invariant under T because T commutes with every polynomial in T. That matters because we want to keep restricting T to smaller pieces without breaking the operator. It is hard to study an operator on a subspace that it refuses to stay inside. Now look at T minus lambda 1I on R1. If R in R1 is sent to 0, then R lies in the null space of T minus lambda 1I. So certainly R lies in G1. But R1 intersects G1 only at 0. Because V equals G1 direct sum R1. Therefore R must be 0. So T minus lambda 1I is injective on R1. Because R1 is finite dimensional, injective already implies invertible. So lambda 1 is not an eigenvalue of the restricted operator T on R1. We have removed lambda 1 from the remaining piece, which is exactly the kind of progress mathematics occasionally permits. Any eigenvalue of t restricted to R1 is automatically an eigenvalue of t, because an eigenvector in R1 is still an eigenvector in V. But lambda 1 is no longer possible, so the eigenvalues on R1 are among lambda 2 through lambda m. Now apply the same argument to t restricted to R1 and the eigenvalue lambda 2. That gives R1 equals G2 direct sum R2. Then repeat again and again. Each step peels off one generalized eigenspace and leaves a smaller invariant remainder. This is just recursion with better handwriting. Chaining the decompositions together gives V equals G1 direct sum G2 direct sum and so on, plus a final remainder Rm. But after removing all distinct eigenvalues, the restriction on the remainder has no eigenvalues at all. On a non-zero complex finite-dimensional space that is impossible. Therefore the final remainder must be 0. So we have proved the theorem. V is the direct sum of the generalized eigenspaces corresponding to the distinct eigenvalues of T. Each generalized eigenspace is T invariant, because T commutes with T minus lambda Ji to the n. On each Gj, the operator T looks like lambda J times the identity plus a nilpotent operator Nj. So once we choose a basis adapted to the direct sum, the matrix of T becomes block diagonal. One block for each generalized eigenspace. That is exactly the doorway to Jordan form. We have not reached the castle yet, but at least we have stopped walking into the moat. So that is why generalized eigenspaces decompose the space. Fitting decomposition splits off one eigenvalue at a time, and repeating the process finishes the job. Next we zoom in on each generalized eigenspace and see how nilpotent structure turns those blocks into Jordan blocks, because apparently matrices were still not segmented enough.